we can look at the universe, and I agreed with a lot of what Peter was saying earlier, that I particularly do not subscribe to this idea, that you cannot get a message from looking at the stars. He was quite correct on that, and I do not subscribe to that view, which people variously call light in transit theory, and sometimes people call it mature creation, but you need to be careful using that word because people don't necessarily mean the same thing when they use that phrase. So how do we understand the cosmos? Clearly, it's very, very striking. Psalm 19 says it all. When we come to the scriptures, it does lead to a lot of issues, because if you're going to take the position of a young universe, you've got to say that all these wonderful structures were made after the Earth. So what is the route forward for an alternative where you're coming from a young universe approach? I have no problem with the Einstein field equations. I am in awe as to the brilliance of Einstein and many of the men who worked with him afterwards. I am a mathematician. I'm not saying that I've worked in my own research with the field equations, but they are very, very well put together, very brilliantly summarize the issues which are involved. But of course, as with all differential equations, highly nonlinear, there are initial conditions which you do not know. And that's very, very important that we stress that. You do not know the initial conditions. And you do not know, therefore, what are the various parameters which need to go into those. Well, you can either look upon it as 10 equations, or some people will say that there is another 4, so it becomes 14 equations. But they are very, very similar in principle, only in principle, not in detail, to the fluid flow equations that I'm more familiar with in fluid mechanics. And if ever somebody was to say to me, look, I found a solution, I'd say, yeah, but what about the other solutions? And often there are a multitude of solutions, not just 2 or 3. There can be a whole raft of possible solutions. So when one considers the mathematical solutions, you've got to be exceedingly careful about this matter of initial conditions. And of course, one of the most important issues is there a finite edge to this universe, or is it infinite? And is there a preferred location, which was mentioned in the earlier talk? There is also one parameter there which has already been referred to, that is the cosmological constant, which is something that Einstein said, that was the biggest mistake I ever made. But then, of course, people have used that later and said, no, keep it in, because we need it. Well, I'll come back to that. That's an interesting whole issue there. Einstein's field equations, of course, are an expression of general relativity, and there's no doubt in my mind that they've been proved to be an accurate description of the way gravity affects light. One of the most important matters, and was actually a hugely important experiment in its day, was when Sir Arthur Eddington saw the solar eclipse of 1919, and he noticed that the stars, of course, when you've got the sun blotted out, you can then look at the stars behind, and the stars appear to be in a different position because of the bending of the light. And there's been many other examples of this. It's really called the lensing effect, but there are many examples now being found where you can actually get one star, this is a red shifted star, in front of a blue shifted star, which is behind it, and it's got bent all the way around it. It's just a marvelous example of this lensing effect. So there's no doubt that, in my view, some Christians have doubted general relativity, and I know some very eminent people who, I'm a bit surprised that they doubt it, to be frank, because to me it's very clearly proved that general relativity is both theoretically rigorous and experimentally proven. So I take very much the Einstein field equations. We had this picture earlier, so we won't comment on that, but there is another version of this which Alex showed when he did a talk in 2012, and I do thank Alex for his very clear presentations, which some of which I've looked back on and got ideas. This is the standard Big Bang model, and we heard earlier about the inflation period and then the settling down to a near critical and then the expanding again. So cosmology is fraught with difficulties. You've only got one universe, as far as we know, and I don't think that that, to be frank, biblically is doubted. You can't compare with similar objects. You can only observe, you can observe only from one position at one time. Nobody's yet got to Mars, but there won't really be much difference when you go to Mars. Slightly, but not much. You need to go to Alpha Centauri and then maybe a bit further to Andromeda, and then you'd get a really different view of the stars. But you'd still be, well, with Alpha Centauri, you'd still be in the same galaxy. Andromeda, obviously, you would be hopping to the next galaxy, which would be interesting. Maybe one day we will, but at the moment we don't have that luxury. Distant objects are hard to distinguish from the background, and distances are hard to measure. I'm not doubting the overall position of distance, which I'll come to in a moment, but they're not easy to measure. The conditions in the early universe can't be reproduced in laboratories. So we don't have a way of testing easily. Even in the parallel sciences of geology, you can't go back and rerun it, but at least you've got the rocks and you can look at them, right? You get the rocks from the moon, you can look at them, you can sort of find out what's in them. You can, mess about with them. You can't do that with cosmology. You're very, very limited as to what you can do. Biology, of course, you can do an awful lot more experimentally. So we must hold our hypotheses tentatively and with humility. So what I'm presenting here is not coming in and saying, oh, Peter's wrong, this is wrong. I'm not doing that at all. I'm just simply saying, here, guys, there are ways of looking at this which might lead us to a different conclusion. That's what I'm doing, right? So please don't think that I'm coming in saying, I know, I certainly don't. But I do know a little bit about the mathematics. I do know a little bit about the physics. And I just suggest to you, let's be open to a frank and careful discussion. Now, the evidences for the Big Bang are presented, as was intimated earlier, the Hubble expansion, the primordial nuclear synthesis, which is to do with the making of the early elements, hydrogen, helium, lithium, beryllium, and then a cascade, it's reckoned, of the formation of heavier elements later. And then, of course, the important cosmic microwave background radiation. So I'm not going to say a huge amount about these because clearly I'm not actually trying to say that I accept them, but I do nevertheless need to present to you carefully what is presented by the Big Bang theory, or it's sometimes called, as was done earlier in the talk, the standard cosmological theory. So whichever words we use, I'll use them interchangeably. So I need to just look at these three bits of evidence, because I agree that very much you've got to take account of evidence. But I'm going to turn that round, and I'm going to say, if you're going to go for a Big Bang theory, it must take account of evidence. It cuts both ways. And the evidence, in my view, doesn't really fit very well. It fits in some areas, but not in all. There's clearly this trend, we don't deny it, which is at the very large scale when you're looking at redshift. To get to those distances, you use C5 variable stars, that's pulsating stars, and I accept that basic position that, as far as we know, the brightness of these pulsating stars is almost invariable. It's very, very unchangeable. So it's like looking at car headlights. You can judge by the faintness as to how far away those pulsating binary stars are. And so when you find them in Andromeda, you can work out then how far Andromeda is away from us, and so on and so forth. And that's the sort of, you use for much smaller distances, parallax, but that only works up to about, well, of the order of 30 million light years, somewhere in that order. And then you're moving out with the binary pulsating stars, and then you finally come to using the Hubble parameter, which does seem to give you a pretty good idea as to the very large distance scales. We need, though, to be a bit careful, because you're looking at light which has basically shifted to the red side due to the fact that there's been expansion and acceleration with it. And although I personally think that they are essentially about right, we just need to be aware that you are doing some interpretation here. Redshifts would be expected if galaxies are moving away from us, moving towards, comes together, moving away, moves further apart. Redshifts are interpreted as being caused by the expansion of space. And just to remind you, this diagram was referred to when we had the earlier talk. Please don't think that you're dealing with 3 dimensions in that theory, you're dealing with 4. And it's very difficult to think of 4 dimensions. But it's posited, right? The posit of the Big Bang theory, or the standard SEM model, is that nothing's going to be in a preferred location, simply because just as if you imagine a 2-dimensional surface, if you're sitting on that balloon, you wouldn't be aware of a preferred location as it expands. Well, we're on a three-dimensional, quotes, surface of a 4-dimensional hypersphere. That's what's proposed. And it's a fair enough. It's mathematically, it makes sense, even though I can't actually see it. But mathematicians sort of make analogies, and that's fair enough. It's abstract, but it could well be true. So there's no 3D natural center. And of course, it's based on the fact that we're somewhere here, but really you should put the Milky Way there, because you're talking here about gigantic distances. And we're finding that there is redshift evidence. By the way, there's most of the galaxies, not all, but most of the galaxies are redshifted. And we find that the Hubble constant seems to be in the region of about 71 kilometers per second per megaparsec, which I've written down for you there. So that's the formula that is used. So I have no particular problem with that. But just remember, though, that there could be other causes for redshift. I don't personally think that these ones are very likely. So if you don't mind, because of time, I'm not going to comment on them. But this is very likely. But we just need, and I don't think that decreasing speed of light is very likely either. That's what Barry Setterfield has proposed. But we just need to be aware that special relativity, of course, gives you also an effect on frequency or wavelength of the light. That's just simply due to motion. That's not due to expansion. And of course, gravity is going to also come into it. In my view, I think it's very important. We also need to note some things. By the way, I've got some books which I will come to at the end. These books are for sale, but I'm just going to mention a book here which is not for sale. It's my own copy, so please don't run away with it. But I was very interested when I read this book, Redshift by Stuart Clark from the University of Hertfordshire some years ago. And he is not, as far as I know, a Christian, but he mentions in his book, and he's not the only one who's mentioned it, Halton Arp has mentioned this as well. He's died now, but Halton Arp also had grave doubts about the SCM. We find that the redshift tends to be quantized. Now, I won't go into detail then on this because Peter had a very interesting slide on this earlier, which also mentioned the grouping, the clumping together of the redshift. It's not exact, but there is definitely a movement towards a particular value, and then you go out a bit further and there's a movement to another value. Now, I'm not saying I know, but that would imply that you've somehow got a shelling of galaxies, which, by the way, would then suggest that there is something preferred near where we are. So that idea of a Copernican principle applied on a galactic, or sorry, I should say a universe scale, may be questionable. So just have that in the back of your minds. And it was very fair what was presented earlier, because that was mentioned as something which does need to be considered. I'm not going to say a lot about this because basically I can't do everything all in one talk, but the idea that all the elements are produced neatly by the Big Bang isn't really true. What they do have is, it is true, and this is fair, that 75% hydrogen, or roughly in that maybe 74 helium, but it's hovering around 75, 25, sorry, it should be 24 because you've got to leave enough room for a few others, so that should say 24 there, but it's roughly in that region. And the Big Bang model is saying that elements come together in about the right values that you'd expect. And this is what we find with in stars, as they would propose that they develop. However, the formation of the heavier elements, I don't think is really sorted out. Because, just briefly, and I won't develop this point, we can perhaps deal with it in discussion, but they are bound to say that there is a condensing of those gases and lighter elements to then form the heavier elements. That bit is certainly not shown to be true. Nobody has ever shown that you can form the heavier elements by condensation. And you need to be careful when you read books on this. I'm sure my colleague who spoke earlier would agree with me here, that actually the formation of heavier elements is very, very difficult indeed, because you're dealing here with essentially gases, and you're trying to propose that those gases come together and condense. Well, my physics doesn't show that that happens easily. I'll leave it at that. We'll come to the cosmic background radiation, which is often trumpeted as the major reason why the Big Bang model is correct. Now, I'm not saying that what I'm going to propose in opposition is necessarily the way to go either. I'm just flagging things, okay? And I think some of these are very serious. The cosmic background radiation, as was, let me just come back to that, as was shown earlier, is essentially this picture. That's what we have now. We've actually moved on beyond the Wilkinson map scheme, which it was a satellite which went round for about 10, 12 years, was it? And then now we're on to the Planck one, which is a huge resolution. So at first people were wondering, and when this first started, I thought, boy, how can you really be sure that you haven't just got errors here? And even those who believed in the CMB had some doubts. But I think it's very much showing that the CMB is real. So I have no doubts now that it's real. And it's a very interesting phenomenon. As was said earlier, the resolution is very, very small indeed. And I just want to now just look at this a little bit. You've got to actually, the actual temperatures of this, but you've got to take away the effect of the Milky Way, which is basically what's going on in the middle there. The Milky Way itself is radiating. So when you actually see this picture, you're looking at differences, right? Differences of temperature. Now this is a very interesting picture when you start analyzing it. I'm just going to briefly mention a mathematical construct, but it's a very important one, and that is that you can find what are called evidence of monopoles, dipoles, and you can go up, right up to all sorts of number of poles, where you're looking at whether the data is consistent with some sort of mechanism producing it, right? And the mathematicians have a field day on this, and they run all sorts of what are called moment calculations to work out whether the data is actually demonstrating a preferred location in that CMB data. And the one that is perhaps the most interesting is the 8th dipole. It's not a dipole, the 8th, what do you call it? It's not quadrupole, but it's the quadrupole times 2, so it's octupole. Yes, get it right, as in octopus. So, and this is what is just intriguing. People have written about the CMB an awful lot in the literature, but this is the ecliptic plane, right, which is the plane of the Earth going around the Sun, right? And there is also another intergalactic plane there, which I won't comment on, but that there are also things to do with that as well. But it separates the weaker power in the northern ecliptic hemisphere from the stronger power in the southern ecliptic hemisphere. In other words, it's not totally isotropic. It is essentially isotropic, nobody's doubting that. It's all around 2.7 degrees Kelvin, so there's no doubt that at leading order, it is isotropic. That means it's not dependent on direction. But when you look at the detail, it's not. You say, well, surely, you can't measure it to that extent. And to be frank, I've also wondered that. But unless I'm wildly mistaken, the papers on this are saying that they have a 99.9% confidence level that there is something going on in the data which is not isotropic. So we have an issue here. For the Big Bang cosmology, or SCM, there is no reason why the CMB should be correlated with any features of our local solar system, because there is no preferred location. We know that, don't we? You might say, but this is tiny fractions of a degree. But this has been demonstrated repeatedly by the satellite, WMAP, and also now by the Planck satellite. And they've gone through many sweeps through the sky to check this. So I think there is something here which is signaling that we need to think again. I'm not saying that the route that others have followed is therefore immediately justified, but something is in the data. Remember the redshift? That was also a pointer. This is a pointer. The CMB, which is trumpeted as a proof, it's actually got a little bit of dirt in it, which is forming, in my view, a pearl, which is telling us where to go, that the model needs to be re-looked at. I don't know whether this came through in the references. One of the versions of my little description, it mentioned Longo, but I didn't actually put the reference in. So if you were looking for this reference, here it is, and I've got copies of these papers if you want me to send them. But interestingly, in a paper, I didn't put the date, yes, 2011, not so many years ago, this is another point, that people have looked at the spiral galaxies and looked at whether they're left-handed or right-handed. And they found that there is a parity-violating asymmetry as a result of the overall universe. In other words, when you add up all the parities, it doesn't come to zero. Something is suggesting that there is a movement of the whole universe about a preferred axis, which I find staggering. Now, you could say, well, we don't know, and that's a fair point. But there are little indicators here, particularly the first two. Some other issues with the standard cosmological model. Blue shifted stars are found in an unexpected way, and I'm just going to show you that in a moment. Mature galaxies at great distances. I'm going to look at walls of well-developed galaxies. The horizon problem has already been mentioned, and the inflation accelerating universe. In order to, forgive me, I'm going to, I hope, I'm not being pejorative to people personally, but I am to the SCM. I'm going to use the word rescue. To rescue the SCM, everybody homed in on the vacuum energy term, which Einstein has said, why did I put that in? And Einstein himself then was argued back by others to say, no, you need that. And then Guth, of course, as you saw earlier, said, we definitely need that. But the problem is nobody knows what it's come from. And there is no logic which says from the evidence that there should be such a term. And inflation needs it, and inflation also needs dark mass and dark energy. There is some evidence, obviously, from the gravitational lensing that we mentioned, and I quite agree with the earlier point about the spiral galaxies. There's got to be a huge more mass than just what you see. So dark matter, there's definitely some evidence for it. There's a little bit of evidence for dark energy, particularly when it comes to the supernova, but that's the only bit of evidence we've got, and there's certainly nowhere near the amount that is needed in order to expand the universe further, because it's still accelerating, as was indicated by that famous diagram. Briefly on the blue shifted stars, and I need to have enough time, so I'm going to go fairly quickly here. SEM, Standard Cosmological Model, suggests blue stars formed by condensation of clouds of elementary particles, and as I said earlier, the physics of this is not really established. Okay, people say that they see, star nurseries, but all they're doing is they're interpreting observations of that which has appeared. Now, the appearing may not be due to forming as people think. We need to be exceedingly careful on that. Also, blue stars, as was shown earlier, they're gigantic. They're up to about 130, maybe more, suns. And their power is extraordinary, such that they would normally burn out in 1 billion years at the most. And yet we find them. We find lots of blue stars. Sometimes you find them in a globular cluster, which is of red-shifted stars. What's going on? Something's odd with these. And this is not isolated. You might think, oh, you're just tinkering at the edges. No, I'm not. I'm actually going to repeated observations which are found of globular clusters and other places where you find blue stars appearing. Then, as was mentioned earlier, many spiral galaxies appear the same age with distinct spirals, no matter where they are found on the supposed trajectory of a Big Bang expansion. In other words, if the Big Bang is right, you're looking way out there at 13.7 billion light years, except you never get there, you might get towards it, say to 10, right? And what do you find? Evidence of gradually forming galaxies? No, fully mature galaxies. And then also further in, where you think there's been a lot more time and all the spirals should have just gone and become a mush, you still find them. So everything is looking from an observational position as though they're all roughly the same age. There's certainly indicators here that we haven't necessarily got age. We thought we had age, but have we really got age of galaxies? And something which is really very, very interesting is the walls of galaxies. The Great Wall, it's called, the Great Wall of Galaxies. Now, this could be put as a favorable position for the Big Bang cosmology, and it was done quite fairly and earlier, because people have run models and say, well, you'd expect all the galaxies to be connected, but just a minute. The Great Wall of Galaxies is of the order of, let me get this right, it's 300 million light years long. Now that is gigantically long. So all these galaxies are obviously all connected. And this gentleman, Ku, at the University of California, says the regularity is just mind-boggling. Another person, Davis, says at Berkeley that he admits that if the distributions of galaxies is truly so regular, it is so safe to say we understand less than zero about the early universe. In other words, it's the regular clumping of the galactic matter all connected together which suggests structure. That's what the point is. That it isn't just random, send this galaxy out there, here and there, everywhere. There is an evident structure. Remember I talked about the concentric circles possibility? We're not saying that we know, just that the data, if it is cosmological redshift would then suggest concentric circles. Now we're getting other things which are suggesting great structure. Now, just to show this, I think I have time just to show this. The discovery was made in 2004, almost by accident, and the point here is that this is so far out. This is 10.8 billion light years away, right? So that would mean that this structure had formed exceedingly early, which is very counter the SCM model. Do you see the point? Do you remember that great big, jar on its side? Some of you look a bit bemused here. That Peter showed and I showed earlier, that you had an early universe where basically you hadn't got galaxies, right? And yet this is indicating you certainly did have galaxies, and they're all connected. So that's why it poses a massive problem to the SCM. Sorry if I'm putting it strongly. I hold it with humility and tentatively, my position, okay? But I'm trying to make it clear what the data to me is saying. So you've got great walls of galaxies. Just to illustrate this, this is indicating what the model's going to do. It's looking at these great wall of galaxies, 300 million light years long. Now we're actually looking at the data in a bit more detail. And it's basically showing that there is a structure which is there 10, nearly 11 billion light years away, which is about a fifth of the Big Bang's supposed expansion. So this makes for a real problem. If you didn't understand what I was saying there, this is a very similar diagram to the one that we showed earlier. And basically there is a redshift desert here. And the model doesn't fit because you should be just forming the galaxies at this point. Whereas in fact, what's showing, because we're going backwards of course here, this is the 10.8 billion light years away, you've already got the galaxies all structured together. Something is wildly wrong. Not just tinkering at the edges now, we're actually looking at something quite majorly wrong with the Big Bang. We mentioned this earlier, that the SCM has a light travel problem that was solved by the notion of inflation. I personally think that there is a big question mark over that suggestion. But it is a problem that the SCM has a time travel issue because, as was said earlier, the total amount of time needed to cross the universe is much more than the 13.8, or double it, 27 billion light years. 27 billion light years that you need to go back and forth. So, the 27 billion light years that you've got available is not sufficient to go back and forth across the whole universe. So, we have issues to do with the expansion, and if you don't mind, I'm going to not dwell on this because this was already discussed earlier. And that we need an expanding universe. I'm going to miss that slide out. I'll just speak to it. Some years ago, Alex showed this slide from the papers which have been produced by the supernova group, which actually shows that you need to have an expansion of the geometry with a little bit of mass to get you into the region where you're going to actually get a small growth, but a sufficient acceleration to actually match the data that is observed. And the only way to actually get that to work is to come back to the cosmological constant. So Alex Guth brilliantly defends his position, as was mentioned earlier, and he has these little cartoons in his papers to make his point, which is fair enough. And he says at the end of his paper, which you can find on the internet, that the inflationary universe, in his view, is in great shape. He's playing on words, of course, there. For particle physics, he says, a cosmological constant is a mystery. Where could such a small number, which is all you need to tweak it, come from? And nobody knows. And it really is an artifact. It's put there, not with any evidence really to support it. The only evidence that they have is that there is an energy going on, and we've got to find out how to match that data. So we tweak this little value, but we've no reason to say that that value is correct. So now coming to the proposal, we are dealing here with general relativity. We're dealing with time and clocks. I have no problem with general relativity. We're dealing with the notion that according to the SCM, you're dealing with a four-dimensional expansion which has no edge. Remember, I had that diagram earlier. But the alternative cosmology says that there might be a center. Why should we assume that there is no center? That, of course, is something which is abomination to many in the classical, secular, cosmological world. Could there be a natural center? And if there's a center, could there be an edge? And now we're dealing with 3 dimensions. So we're back to something which you can actually much more readily follow. Because before, we weren't dealing with 3 dimensions. So whenever people show you a diagram of the Big Bang, they're not talking about 3 dimensions. They're talking about 4 dimensions. 3 dimensions plus time. So you cannot ever say that you're dealing with a 3-dimensional ball. Yes, they will say that the universe 3-dimensionally in the past was very, very small, but they won't be talking about the size of the universe now. So they won't be talking about a finite universe necessarily. You can have an infinite universe in that model. It may not sound plausible, but that's what is said. Now, we're going to bring in the thought that there could be time dilation. What do we mean by time dilation? We mean that there is gravitational effect on light, which we know takes place with the gravitational lensing. But now we're going to talk about it on a cosmological scale. That's what's now being proposed. So it's not that the SCM, ladies and gentlemen, don't agree with gravitational effect on light. That's not the point. What they would say is that there is nothing on a large scale which has taken place. So that's what Russ Humphreys proposes in his original book, which came out sometime in the 1990s. There's another book here, which is John Hartnett, who's at the University of Western Australia, who's done a lot of work on another model, which I'll come to. The Humphreys cosmology speaks about ordered stretching with a natural center. Unashamedly, he bases it on a number of scriptures because he believes in scripture. Now, do I believe in scripture? Most certainly I do. When something is repeated as this principle is, many times through scripture, many people have thought, that seems to be significant. Now, you need to be careful here. We're not talking about stretching necessarily big time now, but that there was stretching in the past. This is mentioned, if you want the references, you can look them up, but I can send you the slides if you're interested. But this is in lots of literature from the young cosmology gentlemen who've looked into this. In case you're wondering about the fact that it says heavens, it actually says that the raka in which he placed the stars in Genesis 1, in Genesis 1:8 it says he called the raka heaven. So I think there's quite a big case here for saying that God literally stretched space. And that raises issues as to what space is. Please also note that in Genesis 1:6-8, it talks about waters which were above the firmament, the raka, which he also called heavens. Which, just simple logic says that there are waters out there on the edge of space. That's the position. that these gentlemen come to, and indeed I agree with it. We also get some interesting references to do with the future, which we shouldn't be afraid of. I was blessed this morning by what was said about Acts chapter 1 by John Lennox, and he said we shouldn't be afraid about what Scripture says about the future. We don't know all the details, but it certainly is quoted this very thought that the space, the heavens, is going to be rolled up like a scroll. I find that fascinating. Now, we are not saying that we know, but just supposing that is to be taken as a lead. Just to mention that from outside Christian circles, I mentioned Halton Arp. I found these two books exceedingly interesting, but they are very controversial. If you talk about Halton Arp in a secular cosmological meeting, you'll get hounded out of the meeting. You won't even be allowed to speak. Halton Arp was a no-no, because after all, he was not going the route of everybody else. Now, he may not have got everything right, but what I found fascinating about his literature is that he shows case after case where redshift is not properly understood. And he does mention, albeit he doesn't develop this point, that there is a quantization of redshift, which Stuart Clark also refers to in his book. I haven't got Halton Arp's books here, I've got them at home, but I was limited as to what I could bring with me. As it was, I was very near the limit. So, I won't spend time on this because we're not actually talking about anything to do with motion or special relativity, but we are talking about the third, which is that the clock G from a distant galaxy is affected in terms of its time by the fact that you're dealing with expansion, but expansion involving a preferred location with lots of mass near the center. So let's now come to this point. Sorry, I thought I had something wrong there. That's okay. So the clocks at rest close to a gravitational source tick slower. A strong gravitational source at the edge of the universe would cause the observed redshifts, but that clock would actually go the wrong way. So that's not going to work. And gravity does not affect clocks in a homogeneous universe, so we've got to go to an inhomogeneous universe to get any effects which might be useful to us. So what Humphreys then considered was a strong gravitational source, which he calls a gravitational well, which is near the Earth. Now, when we put near the Earth, we're not talking about anywhere near the Earth, literally. If we say that we're at an Alpha Centauri distance, which is about 4 or 5 light years away, somewhere in that region, then we're close, right? It's going to take you 4 or 5 years traveling at the speed of light to get there, but you get the point, right? We're not dealing with anything to do with literally, perhaps I shouldn't have put near Earth, probably should have just put near the Milky Way, right? So you're talking about no, sorry, I should have put, well, you could come within the galaxy, but let's not go there. You're actually talking about initially the gravitational gradient, which is close to the galaxy and could be even coming a bit closer still within the galaxy, which is why I mentioned Alpha Centauri. So we're dealing with three-dimensional expansion, and the suggestion is that what was done in the beginning, we don't know, it's God's affair, he hasn't told us, but could it be that there was an expansion on that day 4? Now, it sounds very appealing, but there are issues. We cannot just sort of simply say, this solves it. You need to be exceedingly careful about a triumphalism, which I believe is dangerous on both sides of this debate. Remember what I said earlier, that there must be a humility. The model may be completely wrong. It may be that the Lord just simply spoke it into existence and there were the stars. But I have a similar misgiving about that position, Because then that would mean that if I was to get my big telescope out and look at the stars, that I'm not getting a proper message from them, which is the point that was made earlier. I totally agree with that point. So therefore, I think we are beholden to say that the stars are worthy to look at, they're worthy to examine, they're worthy to gather the light from, and they're worthy to do scientific analysis on, right? In other words, they're not telling us a false message. So God has said. He's said to us what he's made, and he's giving us the liberty to examine those stars. But of course, we don't have a lot to go on. The model is effectively a white hole cosmology, the opposite to a black hole. Black hole is when you have all the stuff going in. White hole is when you have all the stuff coming out. There's a big resistance, of course, to a preferred location because people think, oh, you're going back to, Galileo and all the debate. No, you're just simply saying that on a universal scale, that there is something which is rather preferred near where we are, which I don't think is a bad point. It does resolve clock differences, and it also, of course, doesn't have any appeal to dark matter and dark energy, but the time dilation of nearby galaxies isn't resolved. In other words, what we saw earlier about a supernova explosion quite close isn't explained. So it doesn't resolve all the issues. On its own, though, there is another problem. It doesn't deal with the cosmic microwave background radiation. So quite justifiably, people have said, well, it doesn't deal with the data. Well, it deals with some of it, but it doesn't deal with significant points. Well, that's been thought about. If you now have something which is a CMB and waters above at the edge of a finite universe, this now is a different proposition. If you like, it's a modification, but it's not without some justification. You say, but nobody's observed the ice. Well, that's true. But then if you take seriously what it says in Genesis 1, you are led to believe that waters are there. With the Milky Way close to a natural center, it would explain the residual anisotropy of the CMB, that's meant to say. Humphreys proposed this and explained even using this, which I can't go into here, but you can find out on, if you want to email me, I can send you literature on this. But Humphreys actually used the notion of waters being on the edge of the universe to explain what had been noticed on the Pioneer craft as it left the solar system, that it wasn't leaving at the velocity that people expected. It was being accelerated just by a small amount, and nobody could work out why. Now, it may not be that this is necessarily what caused the Pioneer to accelerate. We haven't proved that. But he did show that it's feasible that there is a background acceleration force going on because you've got waters on the edge of the universe. And you're not talking about a small amount. You're talking about something like 20 times the whole mass of the observable universe in ice on the edge of the universe, which we can't see. So in a sense, it's dark matter, but in a preferred location. Now that might sound a little bit odd, but it's not necessarily invalid. It is an initial condition, which I would say is no less contrived than the lambda is, in my view, a somewhat contrived artifact in the equations that we started with, the Einsteinian equations of relativity. So gravitational time dilation with waters above actually leads to an interesting issue to do with time. So I'm just telling you what's done. You can fire at it. You can say it's not possible. There are all sorts of people out there who are certainly not liking what Humphreys is doing, but it's an interesting situation that he's dealing with here. Just let me bring that other slide up. This paper has been published in 2008, and another paper has been published in 2014, where he specifically shows that it deals with the CMB. So just coming back to what he is proposing, this slide. It has a timeless zone. It resolves the issue of starlight by having all stars emerging, as you will see, on the fourth day. It agrees with the CMB, and we're going to now look at a little video which is quite brief to close with to show this. It talks about a gravitational potential which is set up in the early creation. Then there is an expansion which he takes literally, as I mentioned earlier, which brings us to where we are now. And this means that it is similar to saying that you've got clocks going at different rates, with basically saying that everything is going on out there in the lighter part of the universe on a different clock time than things happening near Earth. So you may not like that, some of you, because you feel that time should, and this is a point against it, so I'm being fair to those who oppose it. Those who would oppose this would say, but time cannot be different if I'm sitting out there on the edge of the universe, or whatever the Lord's doing on the fourth day, than the time near Earth. Now that's a fair point, but if you don't have this, I don't think there's any possible way of resolving the conflict that you have between processes which evidently are taking time further out, away from Earth, than our normal solar days here. So I take the view that the day is to do with the day on Earth. And I actually do find that there is something appealing in this model. The expansion of the waters above, as I mentioned, 20 times the mass of the visible universe, results in a timeless zone. And then he argues for the stars which have been made and spread out, but with time almost stood still in Earth, then appearing on our fourth day. So let me just briefly say, as I close, I've got 10 minutes time for discussion. I haven't been able to deal with this because, to be frank, it's enough just dealing with Humphreys' model. But John Hartnett wrote a book saying, well, there are all sorts of other possible, what we call metrics that can be used. Why couldn't we go for a 5-dimensional metric which involves speed? This is this one, where the space velocity leads to another location because it's TdV. So it actually then becomes an issue that you've got a 5-dimensional space. It's called the Carmeli metric, developed by an Israeli scientist. And he is saying that this is plausible, but of course it's no way really of testing that one. I think he makes some very interesting points, but I wouldn't say that that is in as strong a position as Humphreys' model. So my conclusions, and I'll open it up for discussion. The SCM is a model with many assumptions. It works for the understanding of some development of an expanding universe. And if you notice, I'm not dismissing the idea of expansion. In fact, I think there is a lot of evidence that there is expansion, but that it isn't a natural expansion that is the answer for Christians. A model must be evidence-driven. That cuts both ways. It obviously cuts against in some areas of the model that I've leaned towards, which is the Humphreys model. There are issues with it. But it certainly cuts into the SCM, because the weakest link is undoubtedly the inflation, which was added without any reason for it. Everything was going wrong. So somebody said, well, we've got to rescue it. We know that there has to be some energy. There's a little bit of evidence for this in supernova, which seem to be having more energy than they should have. And so that there was a strong suggestion that, in their view, that there was a reason for doing this, but really they were seeking to save a naturalist framework, I would suggest, that is what's really going on. And of course, the big point is that there is no natural center, and why should you necessarily ignore the possibility of concentric shells of galaxies, which the evidence does seem to suggest. It has very great difficulty in explaining vast galactic structures. I've dealt with that. So the alternative models are not well developed, I accept that, but do be aware that the number of people working in this is a small number. To therefore expect that they would have got all the answers is a little bit rich, isn't it? You need to be aware that you're dealing with massive mathematical entities, which very few people are trained in doing. But I think there is something to be said for these alternative cosmologies. So thank you for listening, and I trust that you've understood the spirit in which I've done this. Not to say that I know that this is the answer, but there is a rich area of research here which I think needs exploring. Thank you.